Well, first, thank you very much for the invitation to come to St. Petersburg, and it's a particular pleasure to be here and visit Professor Huisken and Professor Ipuchkina and to see them again after a long time here in their home city. So, I would like to talk about mean curvature flow in this lecture series, and today I do an introduction into the analytic and geometric properties of mean curvature flow. Mean curvature flow of hypersurfaces. Everything will be in codimension 1 in this course. So let me just recall the geometry of hypersurfaces. So hypersurfaces in a Riemannian manifold. So consider a map F from some manifold into a smooth Riemannian manifold with some metric G bar. So this is a smooth Riemannian manifold with Riemannian metric G bar. And so you should think of this as some map F. And here you have the image. So here this is nn plus 1 with G bar, and here you have f of mn sitting in this manifold. And then we are interested in geometric structures on this hypersurface to control the geometry of this hypersurface. And the important things there is an induced metric. And so this metric G will have indices Gij, and you can compute the indices from the tangent vectors, and the tangent vectors are given by the first derivatives of the map F, and you have to take the inner product with the metric G bar. So if you write it in coordinates, this is just G bar alpha beta at f of x contracted, alpha beta times df alpha dxi df beta dxj, and here x is some coordinate system here, and y is some coordinate system here. And so here xi is coordinates here, and I is between 1 and n, and here the alpha beta I run between 0 and n, and 0 is the normal direction to the hypersurface. So this hypersurface here will have a unit normal, nu, and then you have an induced metric here. And if you have the unit normal, the second thing you need for such a hypersurface, the second important structure, is the second fundamental form, which is the curvature of the hypersurface in the surrounding manifold. So let me denote this by a matrix A. And the second fundamental form can be computed from the second derivatives of this map F. So we have this formula that the second fundamental form times the alphath component of this unit normal can be computed from the second derivatives of this map F. But then, because it's geometric, this is covariant. We have to put in a Christoffel symbol of the metric G, df alpha dxk, and we also have to put in a term coming from the Christoffel symbols of this Riemannian metric G bar. And that makes this formula nonlinear. So there's G bar with respect to the metric G bar, the Christoffel symbols, alpha, beta, gamma, sum over repeated indices, df, beta, dxi, df, gamma, dxj. It is important, I know in geometry sometimes you like to write everything very elegant, you can write this very elegant with the help of covariant derivatives, but because we need to do PDEs later, it is also very important to know how all these formulas look in local coordinates. Now, if you know the second fundamental form and you know the induced metric, then you can control all the geometry of the hypersurface in this Riemannian manifold. In particular, you can now look at the eigenvalues of the second fundamental form. So the eigenvalues of A with respect to the metric G, let's call them, because this is a symmetric matrix, it has real eigenvalues and we can order them. So lambda 1 less than lambda 2 up to lambda n are the eigenvalues, and these are the so-called principal curvatures. And once we know the principal curvatures, then we can define the mean curvature. So the mean curvature of the hypersurface H is just the sum of the eigenvalues, or in other words, it is the trace of the second fundamental form with respect to the metric. So G upper ij is the inverse metric, so we take the trace of the metric. And if you have the mean curvature vector, of course it depends on the sign of the unit normal. If you choose another unit normal, then you get a different sign for the mean curvature. But if you take the mean curvature vector, then it is independent of the sign of the unit normal. And you see, this is just the trace of this formula here, right? So this is just G upper ij of minus hij times nu in this formula here. And if you take here the trace, what you get is the Laplace-Beltrami operator of the map F. This is an invariant object. So this is, let's call this Laplace-Beltrami operator, and it depends on the metric G and it depends on the metric G bar. So this is the Laplace-Beltrami operator from G to G bar of the map F. So the mean curvature vector is a geometric object of this hypersurface, and it is given by an elliptic system of the map F. And now we can define what we mean by mean curvature flow. So we say, what is mean curvature flow? We say that a map F of Mn cross some time interval, 0 up to capital T, into this Riemannian manifold. We say that this family of hypersurfaces so which is a family of hypersurfaces as before is a solution of mean curvature flow. Let's write it like this. If we have that ddt of f at each point and time is equal to this mean curvature vector at the target point. Well, this is mean curvature flow. Okay? So, from an analytic point of view, this is a second order system of partial differential equations. So, and as I explained to you, it is nonlinear. It is, you see, it's quadratic in the first derivatives of f. That's why it's a quasi-linear system. So it's a quasi-linear second order system. And because we have the Laplace-Beltrami operator on the right-hand side, which is an elliptic system, this becomes a parabolic system. Second order quasi-linear system of parabolic equations. Now you have to be careful with the notion of parabolic, because it is not strictly parabolic in the strict sense, because this equation is geometric, so it is invariant under tangential diffeomorphism. So when you compute the symbol, there are some zero directions. But I show you later that indeed it behaves perfectly like a parabolic system. So from an analytic point of view, if you fix the coordinate systems locally, you have a second order quasi-linear parabolic system, but from a global point of view, it is a completely geometric equation, because it is invariant under diffeomorphisms in tangential direction, invariant under choice of the coordinate system. It doesn't matter which coordinate system you take here and which coordinate system you take there. Now, let me make some more remarks. Because of this, because it's a quasi-linear second order system, you can always get a unique solution if you have sufficiently smooth initial data. So I'm not going to talk about the short time solution problem in this course. So just believe me that from this fact here, you can prove that there is existence of unique smooth solutions for short time, only for short time, if the initial data are, for example, closed, if you have no boundary, closed surfaces, or e.g. surfaces with Dirichlet boundary, fixed Dirichlet. So you can fix the boundary, and if the initial data are sufficiently smooth. So the short time existence is completely, more or less completely understood, and it is solved by the implicit function theorem. You have to linearize the problem, and you can appeal then to results about linear parabolic systems to get the short time existence results. The really interesting question is, what happens to these solutions in the long run? How does the geometry of these hypersurfaces change? Now, the first thing that you can say about the change of the geometry is that in all these flows, the area is decreasing. So when you compute from this equation here, we know what ddtf is, and I gave you a formula for the metric here, Gij. Gij just depends on f, on the first derivatives of f, so you can compute ddt of the metric. And when you do this, it's about 3 lines of computations, which I'm not going to do. You get minus 2 times the mean curvature times the second fundamental form as a consequence of mean curvature flow of this equation here. So you use this equation and do the differentiation for Gij. Then you see how the metric changes on the surface. If you know how the metric changes, then you can also compute from there how the measure on the surface changes. So if you take the measure on the surface, on these moving surfaces, and you compute from here, this is just the determinant of Gij times dx. You do the computation, differentiate the determinant, you get minus the mean curvature squared times d mu t. You always get minus the mean curvature times the speed of the surface in normal direction. In our case, the speed in normal direction is the mean curvature. So the first variation of area tells you this formula, which means that for surface with finite area, it means that the total area of the surface is always decreasing. You get minus integral h squared d mu. So the area is decreasing, and in fact it is decreasing in the fastest possible way. If you take some other speed with the same L2 norm as the mean curvature, the area will decrease less, because this is a square of the mean curvature. So we can say this, we can reformulate this and say that mean curvature flow is the gradient flow of area with respect to the L2 norm on the surface. You cannot, with the same L2 norm, you cannot find some other speed which is decreasing the area more quickly. So in this sense, the mean curvature flow has the same relation to minimal surfaces like the ordinary heat equation has to harmonic functions. Right? The ordinary heat equation is the gradient flow of the Dirichlet energy with respect to the L2 norm. It's the fastest way to make the Dirichlet energy smaller. So here, instead of harmonic functions, we consider, say, minimal surfaces where the right-hand side is equal to 0. And then the mean curvature flow is the gradient flow of area with respect to the L2 norm. So you should think of mean curvature flow as the parabolic version of the minimal surface equation, just like the heat equation is the parabolic version of the Laplace equation. Okay? Just in a nonlinear setting. Now, what is the motivation? Why is this flow important? Where does it arise? What are applications? So, applications in physics are in various regards. First of all, you have some of this if you have surface tension phenomena. Right? So if you have surface tension phenomena where the mean curvature acts like a force on the boundary of some liquid or some soap film, and if you have very high viscosity inside your liquid, then a first approximation would give you mean curvature flow. Then very well tested, actually better tested than the surface tension phenomena, is the motion of grain boundaries. Grain boundaries appear in a molten pure alloy, for example, pure metals like aluminium, then when it's just getting solid, then it starts to get solid at various places, and then you have these various grains with different orientation of the metal grid that is forming. And then these boundaries of these various grids, the grains, start to move. And the motion of these boundaries is very well approximated by mean curvature flow. So, or more general, mean curvature flow also appears in other phenomena of boundaries in phase transitions. For example, in these Allen-Kahn models where you have these W potentials and you have this epsilon parameter, if you let epsilon tend to 0, then the phase transition between these two phases that come up in the Allen-Kahn equation moves approximately by mean curvature flow. A further approximation of mean curvature flow comes, it's a so-called, this is for the physicists, this is it's the one loop approximation of renormalization group flow for strings with boundary in the Wilson model. For strings with boundary in the formulation of the Wilson sigma models. This is a bit remote, but it provides an interesting link to Ricci flow, because you can also view Ricci flow as the one loop approximation of renormalization group flow of closed strings within the Wilson model. So this is interesting, I think, because it provides the only formal link that I know between mean curvature flow and Ricci flow here in this renormalization group context. And nobody has, it's a task for mathematicians, nobody has really understood this formal link through renormalization group flow between Ricci flow, mean curvature flow. I think there's something very interesting to explore. And the final thing that comes to mind is mean curvature flow has been used by astrophysicists in general relativity in particular, they have used it to find the horizon of black holes. See, in astrophysics and general relativity, if you have a black hole and then you take a three-dimensional slice through Lorentzian spacetime modeling a black hole, then the boundary of the black hole in the simplest case is a minimal surface sitting inside the three manifolds. And it's very important in numerical simulations to find that minimal surface. And the physicists, using these mathematical models, have found these horizons by starting far out and then using mean curvature flow to make the surface smaller and smaller, decrease the area of the surface until the surface gets stuck on a minimal surface sitting in the middle of the three manifold, and that's the boundary of the black hole. So there are various applications in physics quite different from each other where this model plays an important role. But now I should give you some examples. How does mean curvature flow look like in various examples? So the simplest one is to start with a sphere. So if the initial surface is a sphere of some initial radius sitting in Rn plus 1 with the standard metric, then you have this picture, and the surface will simply begin to contract. Right, it will, because it's spherical symmetry, the mean curvature vector is pointing inwards everywhere with the same speed, and then you can translate this PDE into simply a ordinary differential equation for the radius of the sphere at time t, right? The radius shrinking like the mean curvature, it's getting smaller, so we get a minus sign, and the mean curvature is n over r, and so we get minus n over r of t. This is an ODE, and you just solve it, and you get that the radius at time t is equal to the square root of the initial radius squared minus 2n times t. So the sphere shrinks in finite time to a point, and you can see the time here. The maximal time in this case is the initial radius squared over 2n. So the sphere shrinks to a point in finite time. Notice those of you who may have seen harmonic map heat flow, where you have a map F, just a map, not a hypersurface. And then you can also solve this equation, d dt F equals Laplace-Beltrami operator on the sphere into Rn plus 1. But then something completely different happens, right? Because here, this is the mean curvature vector with respect to the metric at time t. So this one here, this is the Laplace-Beltrami operator of the metric at time t inside the big manifold of F. So in harmonic map heat flow, this would not depend on t. This would be a fixed metric on your initial sphere. So for harmonic map heat flow, it would take infinite time. It would still contract to a point, but because it's a fixed metric in harmonic map heat flow, you don't change this. You would also contract to a point, but you would do it in infinite time. But for mean curvature flow, because it's so nonlinear and it is the metric on the induced surface at the time t, the surface accelerates. The mean curvature gets bigger and bigger as the surface gets smaller, and then it accelerates and it hits zero in finite time. So there's a huge difference between harmonic map heat flow and mean curvature flow. Okay? Now, once you know what happens on spheres, of course, you can then do cylinders. Right? So you have, of course, examples of cylinders where you simply take a sphere and you add one or several dimensions here. So you can take Sn minus k cross Rk sitting in Rn plus 1. And then, of course, you have the same formula here. You have R of t is equal to the initial radius of the cylinder squared minus 2, and now it's here n minus k times t. So you have a shrinking cylinder as the solutions of mean curvature flow. Okay? Now, there are many more self-similar solutions. So let's write down some other self-similar solutions. For example, when you look for self-similar solutions for n equals 1, you find, of course, the circle, just like this one for n equals 1. The circle shrinks to a point. But then you get a curve like this. And you get a curve like this. And so on. You get a whole one-parameter family of curves with more and more leaves. And these were found a long time ago by material scientist Mullin, and then rediscovered by Abresch and Langer, who gave a complete classification in the one-dimensional case. Now, for n greater or equal 2, you get a zoo of self-similar solutions. There's many. Already in the axially symmetric case, I don't think there is a classification. So if you just rotate here the x-axis, the curves, then you get, of course, you get the sphere, then you get the cylinder, but then there's a torus. If you rotate, there's a certain curve which was found by Sigurd Angenant. You can show there is one curve, an embedded curve. You rotate it around, and you get an embedded torus, and this torus moves under self-similarities under mean curvature flow. Then you get a surface which looks like this. If you rotate this curve around the x-axis, you get an immersed torus, which again is a self-similar solution of mean curvature flow and contracts to a point here on the x-axis. And then you can play with a computer, and in fact there is something which looks like, you know, there are incredibly complicated tori that you can create, which all lead to self-similar solutions of mean curvature flow. And there are many others. There's no classification in higher dimensions, even of the self-similar ones. Now, all these self-similar solutions satisfy an equation. Namely, in order to be self-similar, that the shape doesn't change except by scaling, must mean that the mean curvature in normal direction has to be a multiple of the position vector. So you get that the self-similar solutions all satisfy the equation that the mean curvature is equal to the normal component of the position vector divided by the remaining time. So T max is the time where the surface contracts to the axis here, or contracts to a point, and f dot nu is the support function. So you've right. So translating solutions. See, there are solutions which look like this. For n equals 1, this is an interesting solution. There is one. This is now a non-compact solution. So take y here and take x there, and let's take pi over 2 here minus pi over 2 there. Then there is a solution which is asymptotic to these horizontal lines, and I have a formula even for it. Y is equal to minus log cosine of x plus t. So this solution doesn't change its shape at all. It's a solution of mean curvature flow, and the shape is always the same. It's just translating in the plane. And you can find similar things for higher dimensions, except that in higher dimensions the solution cannot be contained in a cylinder. Right? If it was contained in a cylinder, then we know the cylinder is shrinking. Where do I have the picture? Somewhere I've drawn up there. Here. Here's the shrinking cylinder. And as you know, parabolic equations have this maximum principle. If you have two solutions of the same parabolic equation, and initially one is above the other, it will remain like that all the time. So similarly for this mean curvature flow, because it's a parabolic system, it turns out if you have two solutions which are distinct at the beginning, they have to be distinct later on. So if we had a solution which is initially inside the cylinder, it has to remain in the cylinder all the time. But the cylinder dies in finite time here because of this formula. So we cannot have a translating solution which sits inside the cylinder in higher dimensions. Therefore, the translating solution must open up. And indeed, there is a solution which looks like this. Yeah. So here this is again y, and this is x. And it turns out y is approximately some multiple of x squared plus t. So there is something which looks like a paraboloid. It's not exactly a paraboloid, but it has the same growth as a paraboloid, and it moves by translation out to infinity. Those of you who know Ricci flow know that these kind of pictures also come up in Ricci flow. You have similar kind of solutions for Ricci flow. So, is it best to do this wet or dry?
I think that
Dry is better. Yeah. Right, so we have translating solutions. In that case, it's not surprising that there are also some expanding solutions. There are even some rotating ones, but I don't get into those. So there are expanding solutions. And for n equals 1, you get 1 for every angle. So if I have an angle here, then there is a solution which comes out of the angle and moves by homotheties coming out of this angle. And similarly, for higher dimensions, if you can draw any reasonable cone, reasonable means positive mean curvature, and you can prove actually that there is then a unique expanding solution of mean curvature flow flowing out of this cone and smoothing out. And in fact, you can see that in this case the speed is decreasing, and the scaling tells you it's decreasing like some constant over square root of t. So the solution gets slower and slower, but it expands out of this angle. In other words, the flow has some very distinct smoothing behavior. Even if you start with something singular, it becomes smoother in the end. So notice now we have sort of nice behavior. We have solutions which keep their shape. We have solutions which smooth out and become nicer. But also we have solutions that develop singularities, like a shrinking sphere and all these self-similar shrinking solutions. Now it turns out singularities are quite common in this flow. So we have singular behavior. Let's go away from the self-similar solutions. We get all sorts of singularities. I showed you already the self-similar shrinking ones. That's a simple kind of singular behavior. But then you get something more complicated. Namely, you can get a singularity even if the thing is not self-similar. For example, if you start with something convex, you can show that the surface will remain convex. I get to that maybe later. It will remain convex. It will shrink because the mean curvature vector is pointing inward. Here's the mean curvature vector. And then as it shrinks, it becomes more round. And in the end, it looks like a round sphere and contracts to a point. So in the end here, this convex thing will near the singularity, it will look like the self-similar shrinking sphere. So I call this a spherical singularity. Spherical because after rescaling, it looks exactly like that solution, that shrinking sphere that I started with. And it's a theorem of mine a long time ago, saying that this is always true for any convex initial surfaces. All convex initial surfaces have such singularities. Okay? Now, but other things can happen. For example, even for n equals 1, some funny singularity can happen. Namely, if you draw a curve like this, this is a curve in R2, then you see the mean curvature vector in the small loop is bigger than in the large loop. So the small loop will shrink faster than the big loop. So what happens is you get something like this. And then in finite time, you get a cusp. Here, a cusp forming. You get a cusp singularity. The funny thing is, if you rescale this one, if you rescale near the singularity, you look under the microscope, what happens near the singularity, what you see is a surface which looks like sort of like this. And when you look closely, what happens here in the finite part, then you see here that this part converges to the translating solution, which I've drawn over here. So this one, after rescaling, this one here is the rescaling of that one. So we have now two examples where a non-self-similar singularity after rescaling looks like one of these self-similar singularities, self-similar flows that I had on the other board. Turns out this pattern goes on. Namely, if you go for n, say n equals 2, we have this example. But there's also a picture which looks like this. You have initial surfaces that look like that. I call that a dumbbell shape. And now if you make this neck in the middle long and thin, then you have a big mean curvature vector pointing inward, but much bigger than the mean curvature vector here of these two bubbles at the end. And then the neck in the middle will shrink off much faster than the bubble at the end. So you get something like this. And then here you form a singularity which is called a neck pinch. Singularity. And if you rescale this one, then what you see is, if you look under the microscope, because the curvature in this direction is much smaller than the curvature around the neck, you get a cylinder. So you get this shrinking solution. You get S1 cross R, which is this one here. So it's another singularity which after rescaling looks like one of these self-similar things. Now, something very nasty can also happen. Namely, if you now draw an initial surface which is somehow in between this picture and that picture. So if you draw something which has just a small bubble here, then it wants to do the neck pinch, but on the other hand, this one wants to move in very fast, and this one only moves in a little bit. So if you do it just right, if this is too small to make a nice neck pinch, but it is too big to make it into this picture, then this little bubble will get stuck, and you end up with a singularity which looks like a cusp here. So here we get, again, a cusp. But this is a different cusp than the one up here. On the other hand, if you rescale this, well, what will happen? What will happen if you rescale this thing? Turns out you have to be extremely careful. If you rescale around the tip of the cusp, you put the microscope right at the tip of this cusp, then what you see is this translating solution which I was drawing here, just pointing the other direction. But if you rescale near the tip, you go a little bit further away from the tip, and you rescale, you will see the cylinder. In other words, this singularity is very complicated. It looks different at different places, different scales. If you go too far away from the tip and you rescale, you might just see a plane, something trivial. Yeah? Because then you get into the regular region where there is no singularity at all. So in this singularity, it very much depends where you look, where you rescale. And you get different singularity models. This one is what you see if you take this paraboloid far out to infinity, right? A parabola near infinity, if you rescale it, looks like a cylinder. So this is the cylinder that you see near the infinity of the paraboloid. So this is just a zoo of phenomena that I wanted to show you. Now, so I want to make clear that this is a rich theory where you have many phenomena. So if you want to prove something, you have to make some assumptions, because otherwise you have no chance of, you cannot prove estimates, or you cannot hope to prove estimates which hold for all these phenomena. So you have to make some assumptions to single out a class of solutions that you want to study and exhibit one or other of these behaviors. So what kind of assumptions can one make in order to prove something? Now, a useful assumption where you can prove something is that you go back to PDE techniques and say, okay, first I need to understand this equation from a PDE point of view. What can I prove if the surface can be written as a graph of some function? So let's make this number 7, graphical solutions. So suppose we are in the situation where here is Rn, and here is our surface, our hypersurface. Here's the unit normal nu, and the surface Mn at time t is the graph of some function u, and at time t, and u is a map from some domain in Rn, some domain omega in Rn, cross some time interval into R. And then you can ask, what is mean curvature flow in this case? And then you can rewrite mean curvature flow, remember, which was a parabolic system for all the coordinates of the surface. So now we just fix the x here and ask what is the change of the height. And then you can, it's a simple calculation, you can show that mean curvature in this case up to tangential diffeomorphisms is equivalent to an evolution equation for the height at x. T is equal to square root of 1 plus du squared at xt times the divergence of diu on square root of 1 plus du squared in omega cross t. And why is this the right equation? Well, from a geometric point of view, if this direction here is the direction omega, then this here is something geometric. It is just the inverse of the cosine of the angle between omega and the unit normal. So it's adjusting for the fact that we are moving here in omega. Parabolic PDE, scalar, quasi-linear, parabolic PDE. And so one point of view to understand the short-time existence, for example, is to transform the original equation into this setting and then apply the theory of quasi-linear scalar parabolic PDE in order to prove the short-time existence. That's one way you can attack it. The other thing I want to point out is that we have lots of techniques for quasi-linear parabolic PDE. For example, in the book of Professor Uraltseva. And it turns out that for this particular equation, you can, for example, prove by differentiating through a nice equation for this function here. This is the function, let's call it v, which controls the gradient of u. We all know that quasi-linear PDE, it's important to have gradient estimates in order to prove something. You need a priori estimates. It turns out that under mean curvature flow, up to tangential diffeomorphisms, you get that this is the Laplace-Beltrami operator of v minus 2 v inverse grad v squared minus a squared v. Forget a squared is the square of the second fundamental form. It's the sum of the squared of the principal curvatures. What is important is that this is less than the Laplace-Beltrami of v. In other words, v is a subsolution of the heat equation on this graph. And this fact leads to gradient estimates. So this now I have to say a few things about the analysts, otherwise they don't believe me that this is a PDE problem. So you get a nice partial differential inequality in a parabolic setting for the gradient, which allows you to get a maximum principal for the gradient. You have these good terms which allow you have the nonlinear inequality and good terms on the right hand side which allow you to localize these estimates. And all of a sudden you can bring into the context the full regularity theory of parabolic partial differential equations. And this regularity theory tells you that if something goes wrong, it has to go wrong already at lower order terms. It cannot be true that the gradient is bounded and the solution gets a singularity anyway. So you can make use of the parabolic regularity theory and control the solutions in this case. Let me just state one theorem that you can prove this way. So one theorem here, which I proved a long while back. If you have the Dirichlet problem, so if the boundary is smooth, say a C2 alpha boundary, and if phi is a smooth function on the boundary, and if the mean curvature of the boundary is greater or equal to 0, boundary as a set in Rn, then for any initial data u0, say in C0 alpha of omega bar, we have a unique solution u t of this problem here for all positive t, again in C2 alpha for each t, in C2 alpha for each positive t in C2 alpha, and with the right Dirichlet data So you have u d omega equals phi. And as time tends to infinity, ut tends to a limit, to a smooth limit, u infinity in C2 alpha omega bar, which is a stationary solution of the flow, in other words, which has zero mean curvature. In other words, the mean curvature flow approximates the minimal surface spanned by the boundary data phi. So it's another way of constructing the solution of Plateau's problem. So we have sort of complete control in this particular setting, which is not so surprising, but I think it should give you an idea what the flow can do. If you fix the boundary, you have a chance to find minimal surfaces. That's one result you can prove. Now, what can you do if you go away from graphs? Suppose we don't look at graphs, we look at closed surfaces. Now for closed surfaces, I've already shown you we can have these pinching singularities. Lots of things can go wrong, in particular in high dimensions. So let's look at the case of curves. That is already interesting. Closed curves. Now, I showed you already that convex curves, this was in the one-dimensional case, convex curves contract to round points. I'm not going to explain that one. This was first for n equals 1 case was proved by Gage and Hamilton around 1982. But if the curve is not convex, then there is this beautiful theorem by Matt Grayson. Matt Grayson proves that if the initial curve is embedded, then gamma t, the curve at time t, will be convex at some positive time. And then contract to a point by the previous result. And this result is due to Matthew Grayson around, I think, 1988. Yes?
That means that it has
no crossings. Yeah. And well, if it has crossings, it's wrong because of this example, right? If it has crossings, then you get the cusp. Yeah. So the embedded is absolutely necessary. But it's amazing that this result is true, right? Because of the following example. People thought this is wrong and tried to construct a counterexample. And how do they do the counterexample? Try to do the counterexample. Well, they say, okay, let's start with a curve which is contained inside some circle. All right, let's start with a curve which goes like this. This is an embedded curve, right? And it's contained in this circle, which has, say R0 equals 1. And then we know that this circle will be a barrier, right? So I know from here that T max, right? It cannot escape from the shrinking red circle. So the T max has to be less than r squared over 2n, so this is 1/2. So this white curve has to die in half a second. It has only half a second of time. But instead of drawing 3 turns, I could have drawn 1,000,000 turns. So this thing has 1/2 second time to unwind 1 million turns. And Grayson's theorem says, yes, it does it. Yeah? So I think it's a very amazing theorem. The reason is, of course, if I make more windings, then this tip has more and more curvature, and if the curvature is huge, then the speed of the tip will be very big. Yeah? And you can actually put this on the computer. It looks amazing. Yeah? It unwinds, and eventually it will become a convex point. Yeah? Now, how on earth can you prove something like that? Now, the proof that Grayson followed was, I think, 70 or 80 pages long. So what he did was check embeddedness. That's not so hard. Embeddedness remains preserved. And that has to do with the fact if it was ever to cross, it would have to first touch itself. But if it touches itself, you can locally write it as a graph of the same parabolic PDE. And we know that parabolic PDEs have a maximum principle, and you can rule that out. So you can rule out that they ever touch. If they never touch, they have to stay embedded. So that's OK. But then he had to count sort of the inflection points. It's a very complicated proof. Count inflection points, and where the curvature is 0, show that the number of inflection points is decreasing, and so on, and check all the angles and so on. Very complicated proof. Now, for the things that I want to tell you later in the course, a different method of proof turns out to be useful. Namely, you can prove this theorem in a completely different way. And it's sort of the same spirit that was later used by Hamilton and Perelman to understand singularities of the Ricci flow. And it's also the right strategy to understand singularities of mean curvature flow and to understand this theorem of Grayson. Namely, the idea is not to follow all the unwindings of the flow. Don't even try to follow the behavior of this complicated curve. Let it just do its thing as long as it is regular. Only look at it again when a singularity starts to appear, and check out what kind of singularity that might be. Right? Don't even try to prove too much about the flow as long as this thing is smooth. Just check out what could be the possible singularities. And you know there has to be a singularity because it's enclosed in this red curve. The red curve dies, so the time is finite. So something has to go wrong in finite time. And if something goes wrong in finite time, it has to be the fact that the curvature blows up. Because if the curvature was bounded, you could use parabolic regularity theory to show that you get a smooth limit at that finite time and then extend the flow with short dynamic distance. So you know in some finite time the curvature blows up. So you check what happens at that blow up time. So the check at first singular time, t10, and this is a finite time. What is the shape of the curve? That's the strategy. And now to get something about the first singular time, what you need is a monotonicity formula. Right, so it turns out there is a monotonicity formula for mean curvature flow, which looks like that. Let rho greater 0, or I give you the formula. This is 1 on 4 pi t minus t to the n over n plus 1 over 2. It's the backward heat kernel. to the e to the minus x squared on 4t minus t, or you can center it at some other point if you like. You can center it at any time. Be the backward heap kernel. And then there's a theorem which I proved in 1989, which says that you have a weighted energy inequality. Namely, if you take ddt of the following scaling invariant quantity, you take square root of 2 times the remaining time times the weighted area. Remember, the area is always going down. We know that already. The area is going down. Now I claim the weighted area. If you weight the area with the backward heat kernel, it is also going down. Namely, you get minus square root of 2 times the remaining time, integral of rho times the mean curvature minus the normal component of the position vector over 2 times the remaining time squared d mu. Get this formula, which is of course less or equal to 0. It's a computation. You just have to do a long computation, and you see that the weighted area is also going down. Now, this has to do with, this is like, with this scaling, this is like the n-dimensional heat kernel on the surface. Now, if the surface was flat and not moving, then you know, of course, that both these terms here are equal to 0, and it's simply the fact that there's always the same amount of heat if you do the heat kernel on Rn. The amount of heat doesn't change. So this is telling you that in the heat kernel, somehow area cannot, even though the surfaces might contract, like here. The surface can contract, like here. But they cannot contract faster than this. The area cannot bunch up at some point, x naught, at the time capital T, faster than the heat kernel is crunching up. And you have equality in this right-hand side exactly when the right-hand side is 0. But what was it? Right-hand side 0, right-hand side 0. These were these guys. These are the self-similar shrinking ones. So in other words, you can only have equality here if you're on a self-similar shrinking one. And that allows you to classify these singularities. So you use this one, this formula, and you see there's one step I'm going to omit. You also have to rule out the translating ones. It's a separate argument. But you can use this with some extra work, this monotonicity formula, to show that the only singularities for n equals 1 are self-similar shrinking curves. But now you look at the self-similar shrinking ones, and for n equals 1, this guy, Marlin, Abesh, Langer, they've classified them. That's all of them. There are no others. Because for n equals 1, this is an ODE. You can classify the solutions of these ODEs. These are the only ones. And now you check which one of those is embedded. The only one that is embedded is this one. So now you use embeddedness. So singularity must look like a shrinking circle. But that proves Grayson's theorem. So without having to go through the details of what happens to this curve, I just proved that the only singularity that can happen is a shrinking circle. Therefore, the theorem must be true. Okay. And that is going to be for the next 2 lectures. This is going to be the strategy. We now go to higher dimensions and greater or equal than 2. And then we look at surfaces that form singularities. And then we have to classify their singularities. And if we can classify the singularities, then we can hopefully do some surgery, like Hamilton and Perelman did in the Ricci flow, extend the flow and prove theorems classifying certain hypersurfaces in Euclidean space and in other spaces using these PDE techniques and using surgery techniques like in the Ricci flow. But it will always be this spirit to control the flow by looking at the singularities and completely understanding what is the nature of the singularity, and then use that to prove applications in geometry. And in the last lecture I do some applications to general relativity. So maybe that's a good point to stop for today.
Thank you very much.
Any questions?
No, thank you very much. You mentioned that non-compact solutions, cylinders, well, you said that they satisfy maximum principle, and so they are unique, right? Is there a general theorem like this? If I have a complete surface with bounded geometry, then globally unique solution, something like that?
You need something about the growth near infinity. And there are some theorems. So for example, if it is a graph, then if you have polynomial growth near infinity, then you can prove, I think, uniqueness. But I don't think people know sort of the optimal conditions that you need for.
So the cylinder is something like special, right?
Cylinder itself is sort of special because you have not bounded geometry. Right? Geometry is complicated near infinity. Yeah.
I mean there is uniqueness, but some.
Oh, in this class, yeah. Yeah.
And another question: this theorem about shrink into a circle, does it work in the Riemannian surface?
Yes, right. So in the
collapse to
right. So in
or to close geometry.
Right. So if the initial curve is inside some Riemannian surface, if it's a closed surface, then either it contracts to a point, right? So you could have this example, and it contracts to a point, just like in R2, or it could contract to a geodesic, to a closed geodesic.
Which of the methods can you do to prove both?
You have to do it in 2 steps. I mean, Grayson has a long paper proving it with his method. You can use, because the monotonicity formula will still be valid with some lower order. Right, so if the singularity happens in finite time, then you do exactly the same thing. So if the singularity happens in finite time, then you are in this case, it has to shrink to a point because then your curvature blows up. It cannot go to. And if it exists for infinite time, then you have extra information because remember the area. Where's the formula for the area? The length of the curve is decreasing, right? You had ddt of the length of t is minus integral the curvature of the curve. So that means that the double integral of ds dt is finite. It's bounded by the initial length. But you have an infinite time interval now. You're in the case where we have an infinite time interval. So from that you can conclude that as t tends to infinity, kappa must go to 0. And then it has to go to a geodesic.
And exactly to geodesic, or it may, well, in high dimension, I know that there are some examples.
Oh, no. I'm just on a 2 surface. If it's embedded on a 2 surface, then it has to go to a geodesic.
Is it hard to prove?
Well, as I said, you just look at what happens.
Yeah, the curvature goes down, of course, but why is the limit? Why is there just a single?
That you have a single limit. You have subsequences converging to G. Okay. Now to have a unique limit is not true in general.
If
sigma 2 is not analytic, I think, well, I don't know someone has written down an example, but I bet a good bottle of, what do you do in Russia? That you can find an example where different subsequences converge to different, if it's not analytic, you could sort of have the solution wobble around.
You mean C infinity, right?
C infinity, yeah.
Oh.
The limit might not be, yeah.
Can you predict what happens if you have the evolution of a closed surface starting from the convex initial data, and then it meets an obstacle inside, like a rigid body?
Right.
So the closed surface the evolution is infinite time, it shrinks to the point. But if you have boundary data, then the evolution takes infinite time. Yes.
If it converges to a minimal surface, it would take infinite time. Now, if you want to put an obstacle, you have to somehow make a formulation that the solution notices the obstacle, right? So you have to put a penalty term or
free boundary between obstacle and.
Yeah, you could do that.
What can you predict if the evolution of this free boundary would take infinite time or finite time?
If the obstacle has, depends on the sign of the mean curvature, right? So if if you have the obstacle like this, right? If here's your domain omega, and here's your obstacle psi, right? And here is your initial data u0, right?
Yes.
If the picture is like this, of course, this will hit the obstacle somewhere in finite time. It will come through in finite time. It depends how you formulate the problem, right? You might have to formulate it as a variational inequality. You have to say, somehow you cannot use the classical description, right? You have to somehow bring in the obstacle. You can do it with a penalty term, or you can reformulate the equation with a variational inequality, or you can use a level set method. I think if you do it as a variational inequality, what will happen is that you touch, suppose this is the obstacle. Maybe I draw the obstacle slightly different. Draw it like this, then you will have that the surface at the beginning it touches just at one point at the time t0, and then you will have a whole region like this until the solution goes to the obstacle problem for the minimal surface equation. I think in this setting of graphs, I think I can prove that. Yeah. Now, what I don't know is exactly what is the speed of the free boundary on the obstacle. That's a good problem for a student, probably, right? But I think I would bet it's finite speed. Slowly, right? It touches at one point, and then with finite speed, the region will become bigger and bigger where it is attached to the obstacle. That's my guess. I don't think anybody has written that down, but that would be my guess. Yeah.
Any other questions? Okay, then let's find some time. Next lecture.